All right. So we're going to start talking about model analysis overview. Can you guys see, or is it like a light? Yeah. I mean, the weather is good. I was hoping to keep this down. No, that's fine. All right. So we're going to start with model analysis and try to understand different ways that you can. Oh. And we're going to basically delve into the different ways that you can analyze your model. Now, the first, is it good, or I should turn off the lights? Yeah. I feel like it's okay. So the overall, the question that we always have is, so you finish the model, you train the model, and then you basically, you know, deploy the model. And you always have this question that, well, is this model working fine? You know, can I improve it? Is there like the data that we have, will it change in the future, right? Or most of the time, this fourth one is like, since we collected that data, did it actually change anything? Because most of the time you have some snapshot, you download some data, query some data, spend a couple of months on it, build something, but did anything change since I basically got this data, right? So now, when we want to evaluate models, there are two main techniques: black box evaluation and model introspection. So black box evaluation are those types of techniques that they only care about how the model works overall with respect to the metrics. Like if you have like for example, you have a validation data and you have certain metrics that you use and basically analyze your model against them. That becomes black box evaluation. Model introspection, on the other end, are types of techniques that you focus on the behavior, internal behavior of your model. Like how my model works, like how certain layers of my model works, how data basically traverse through my model from the start through the end, and what happens to this data. So one of them, it just looks at the model overall, like how does this model work overall? The other one works like how the model internally works. And depending on the problem that you have, one normally is more important than the other one. Now, when you, there are some tools, for example, like the TensorBoard. Just an example of TensorBoard, in case you haven't worked with it, is if you, like it's pretty straightforward. If you are running a TensorFlow or Keras code, all you need to do is that first, like a pip install TensorBoard, and in your code on your Jupyter, it has like a magic code that you use to basically what it does, it collects logs when your code is running and use that logs to generate this dashboard for you. So you don't need to technically do anything. You just need to let it to listen to your code that's running. And so TensorBoard is kind of like a black box evaluation. It gives you some information around your model, your model's weight, parameters, and stuff like that. And you can basically compare multiple models against each other. But when it comes to model introspection, on the other end, it's where you, this is just an example of like if you have some sort of like image processing, and you're interested to know that when I have this image on the left that goes through my model, what happens at certain layer to this image? What does the model learn, or what's the focus, the attention of my model in this layer? Now, for example, this is an image, and this is some random feature map. So if you look at the also, if you're familiar with CNN or basically there's some techniques like that for image processing, every time that you basically process the image data, you technically learn certain features, and you can visualize that. It is showing this called activation map. This is the output of a certain CNN layer, certain basically convolution or certain filters that you have. And so this is like, if you map this, visualize the activation map, this is what you see. Now, if you pick this and put it back on the image, what you will see basically is that these two regions, and if you're looking at these regions, are the part of the basically image that the dog face is kind of like and legs are like white colors. So that filter basically, it tells you that it focused on this, like this maybe white color, you know, in the image. So model introspection, the idea is like this. So you basically try to look at the internal behavior of your model to understand that why, for example, my model made a mistake. Did it learn? Was it able to focus on the important part of the data or not? So that's the idea. Now, we can look at the metrics, you know, like you have performance metrics, and which we all work with, like, you know, like accuracy, F1 score, just type of things, just like a performance metric. You also have your optimization objectives when you develop these models, which you have certain basically types of like gradient descent, ADAM, or optimization objective that you're using to train these models. And it's also important for you to just remember that the difference between this model, this objective functions and optimization basically technique, that and how or when you should use one versus the other. The thing is that when we are looking at this metrics that you have, most of the time this metrics that you are using or we are using in day to day, it's kind of like a top level metrics. That means you have a validation data or you have a training data and you just report what's the AUC on this, what's the F1 score on this. Those are called top level metrics. What you need also is that a slicing metrics will focus that on maybe calculating the same score that you're using, but not across all your data and across different slices in your data. And we're going to talk about why we should care about slicing more than what we think. So there's also a library, again, as we talk about TensorFlow in this class, called TensorFlow Model Analysis, TFMA. That basically TFMA, it has out-of-the-box options for you to do the data slicing and model analysis. So if you have a TensorFlow model, for example, and you want to see that, I want to do analysis on this model to see that if this model is good across all possible data slices, you can import TFMA, you load your model, you load your data, you pass certain columns to it, and you say that I want to slice it, and it basically what it does, it creates like a group by across your data sets and runs the prediction on those and creates some sort of comparison table for you. I'm not going to talk much on TFMA, but one of the things that TFMA gives you is that, don't get distracted by this. So it basically reads the data as like a TensorFlow example. It makes some prediction. This is slice keys are the columns that you select and you want to say that I want to slice over. That's what it means. Custom extractors. So if you have certain code that you want to run it for your slicing or for your evaluation. And what it does as out of the box, it has series of evaluators. So that combines like a visualization and stuff like that. It also can get your custom evaluation. So if you want some more basically custom made evaluation technique, and writes all of that to a result with a dashboard for you. That's the summary of what happens in TFMA. Now, we say that there's a TensorFlow, like a tensor board, and there's a TFMA. And what's the difference between these two? And a good example for comparison, the one on the left is tensor board. So tensor board is good when you have streaming data, like a model is training or model is running just some sort of like a streaming data, and you have multiple models and you want to compare those. That's tensor board. TFMA, on the other end, focuses on one model across different snapshot of times. Like this is the same model, different versions across different timestamp, and it does the comparison for you and says that, like, it gives you some summary of what happened in different version of the model. So if you have one model, you want to compare it across time, TFMA. If you have multiple models or this stuff, streaming data becomes tensor board. Now, aggregated versus sliced metrics. It's a good example of why we should care about the slicing. When you're looking at RSC curve, so you see something like this and you're like, well, my RSC curve looks really good. So, I'm happy with it. But if you slice your RSC curve, like in two segments, it's just an example, you might find that there's a segment A on top, there's a segment B. In your segment B, it's doing really poorly, right? But because segment A is higher, on average, basically what you say, you pull the result up. So that's the main problem with like some sort of like aggregated top level metrics. Because it's aggregation, you actually don't know if this model will work for everyone. And especially if you have a some sort of like an imbalanced customer data. Some customer you have more data versus some customer you have less data. Most of the time, the customer that you have less data, they don't benefit from the new model version that you have developed if you are not careful about it. So, and again, this is just a summary of pool pass versus TensorBoard versus TFMA. Now, I'm going to pass from this. This is just a code. Again, review it yourself to use TFMA. But this will be the output of what you get from TFMA. So on top, it has options to select a column and types of slice. And across all the slices, it returns you the accuracy and whatever metric that you are using. So that becomes a good identification for you that to understand if your model works the same for everyone. Now, for example, what you can see here is that, so this starts from, I think it's like a 24 hours. Every one of this, I think, is 1 hour, if I'm not wrong, based on what I see here. And what you can see here is that there are certain times of the day that your model accuracy is higher. And there are certain times of the day that your model accuracy is low. Right? It's like this is like a trip start hour prediction or something like that. I don't know what's exactly goes on here. But if you have a knowledge like this, if you have this idea of like, I know when my model doesn't perform good, you could basically maybe have some hybrid basic approach that if we are within this certain basically time window, you could have an additional way of processing the data because you know that your model is not performing. Whereas if you just look at the overall accuracy, you're like, wow, the model was perfect. Right? But this way you have the idea of like what could go wrong. Now, the next thing we're going to talk about is going to be model debugging and just overall how you can debug your model or how you can understand if something is wrong with your model. So the first thing we're going to talk about is the definition between robustness and generalization, okay? So these two terms are kind of like, might sometimes be used together, but they're actually pretty different. Generalization is that my model is generalized. That means it can address all sorts of data. But that doesn't mean that my model is robust, right? Robust means that your model can deal with all sorts of random data, all sorts of noisy data. It doesn't break. That's the definition of robustness. Generalization is just the idea of like, well, my model can address all group of data. It's just generalized. So now, what will happen if you pass slightly like a perturbed data, noisy data to your model? What happens to the result that model predicts? Like, let's say you have a model that gets the data and says accept loan or reject loan. What happens if you just turn the knob on one column? Will it change actually the output of the model? Like if it's a slight change into features, will it have a high gradient? You don't want a model like that because if you perturb a data, but the gradient of that perturbation is really large, that means your model is pretty sensitive. Right? So you don't want to see something like that. Now, when it comes to robustness, again, just there's other types of metrics that you cannot measure them during the training. It just comes post-training. It's you basically split your data and you're going to run certain tests. We're going to just name the test right now. Then when it comes to model debugging on the other end, debugging becomes when you want to deal with any problem that you could have overall system, just like an ML system has like as a whole that becomes for your debugging part. And that also comes as part of the software and software practices that you have. So again, there's all different robustness, model robustness versus the debugging. So you use the debugging in order to figure out what's going wrong. Now, when you want to debug a model to see that if this model is good from software perspective, from ML as a whole, as a framework, it's like a good model. You need to look for certain things. One of them is opaqueness. It's really important. At least I personally believe it's really important that if your model make a decision, you need to be able to justify that decision. So you need to be able to say that. So let's say again you have an application in your bank, and then it accepts or rejects loan, and someone comes and says, "Why did you reject my loan?" You need to have a justification that why did it reject it. If you just say that, oh, my model said reject, then that's not a valid answer, right? So opaqueness means that if you look at the result, you can basically understand it's not vague, And social discrimination is really important. You need to be sure that your model doesn't discriminate against different people, different groups, different ethnicities. Security vulnerabilities. Well, is this model basically secure overall? Like, can someone break into it, or can someone hack it? Privacy harm, on the other hand, is kind of like can someone steal information from this model, like membership inference, or like a reverse engineering the model overall, stuff like that. And model decay, well, and that part of debugging, is this model decaying? Is like how fast this model will decay, how strong is this model, like for how long could we use this model? So in order to do this debug and answer questions like that, there are a couple of ways that you can do that. One of them is like a benchmark models. And that's a really good techniques for a starting point. If you want to debug your model, benchmarking is a pretty good place to start. The other one is like a sensitivity analysis. And the other one is residual analysis. So sensitivity analysis, we're going to talk about it further, is the idea of like how sensitive my model is to the features that I have. Residual analysis, the idea is like, if I look at the errors that my model generates, is there a pattern in this error, the errors that my model has? If you have a model that the errors, there's a certain pattern in the error that you can predict it, then that's not good. Because the errors should be technically random. If you look at all the errors that you have, it should have randomness. If there is some sort of like a pattern in the error that you could predict, that means you can improve that model. You don't want patterns there. You want randomness. Now, for benchmarking, again, it's easy way. You just compare your model against certain benchmark, and this could be a starting point for you. When it comes to sensitivity analysis, the first thing that you can do is that create a simulation data, some data similar to what you have, and pass it to your model to see that what will happen to the result of your model. You can pass data that your model hasn't seen before and see that what will happen over there. So that becomes like a way for doing sensitivity analysis. There's a tool called What If. I don't know by whom. I wonder if it's Google also. What If is a pretty cool tool to play with. So basically you load your model and data set, and it has this idea of like what if I change this, what if I change that, and what will happen on the output of the model. So it's a pretty good tool for just like a playground to just see if your model has sensitivity to certain features that you have. Then the next thing is going to be random attacks, and random attacks is an easy way to see if your model is going to fail in production, right? So what you do, you basically expose your model to all sorts of random data, and try to see that if it's going to produce certain errors, or if your model is going to basically produce NaN, or basically if it's going to break or not. Right, so that becomes the idea. Like you just release a lot of random data on your model. It helps you with finding unexpected software bugs. And then there are some other ways that you can do basically for your model debugging or analysis. One of them is partial PDP, partial dependence plot. There are a couple of libraries out there, but I think the PD box and IC box are probably important ones or good ones. What it does, it gives you some sort of like a comparison between features against each other. So maybe one feature against the other one, or two features against the other. It's kind of like it tells you that how these features interacting with each other, and then what's the impact it has on the output. Then the next question is, well, how vulnerable your model is with respect to attacks. Okay, so attack, it is something that's important to know is that the attack that if your model actually being hacked, that hack the result for a certain application, it could be pretty bad. Especially if your model contains sensitive data, it could be pretty damaging. So the idea of attack is that they try to fool your model in certain ways. So what you can do when you build ML models is that you can test your model against adversarial examples. You create series of adversarial data, pass through your model, try to see that if it's going to basically behave abnormally or different. And then also you try to harden your model with certain ways that basically avoid hacking. Now, this is just a famous example of how you can fool a deep learning model. So what you see on the left is correct image. What you see on the center is noise. And what you see is what's happened to the result of this classification. So what's found is that for this really strong classification image processing, if you add this noise to the image, it always produces ostrich. Right? So what happens here is that if you try to fool a model and you're able to understand how you can fool the model, you can easily change the output that model basically can produce. And is our responsibility is that when you build a model to test it, to see that if can anyone basically fool this model. So how you can do is that you will create the adversarial example yourself and run it through your model for like a certain number of data and see if there is any if there's any room for you to improve the model. Okay. This is another example. And this one, if you add these stickers like this, it's for this car, self-driving car, and the car will read this as a stop sign, like a 45 speed. All right, so you can see that how it can be fooled. And of course, the spam and spam detection every day. Basically spammers, they change their techniques of sending email, sending spams, because they want to fool those models. And that's why companies like Google, they change that spam model maybe a couple of times a day or once a day. The other thing is that when you go, for example, to airport and your bag goes through those conveys goes through a security check, those security check technically they are doing some sort of like image processing and stuff like that. And you need to ensure that those models basically are they're strong. And I think there was this example of like that someone, I think here, they could have figure out that this, if you have a certain types of knife, the machine will detect it as umbrella. And you can basically carry that, basically take it inside past the security, So it's really important to be sure that you basically test your model. Now, the other thing is that informational and behavioral harm that your model could basically suffer from. Informational harm is any types of damage that leads to leakage of information. That's like an informational harm. Behavioral harm is the idea of like manipulating the data to deceive the model. That's what the examples that we just saw, those are like a behavioral harm. Now, when it comes to informational harm, one of the first one is kind of like a membership inference, and that's the idea of like you try to see whose data was part of the model training. that's like a membership inference. I think if I'm not wrong, the good example for that is that the arguments or basically the course that OpenAI and New York Times they have. Like New York Times basically did, I think at least that's what they are basically claiming. The OpenAI is claiming that they hacked into the system to figure out that if the data was used, which is against the policy. And that becomes membership inference. So you kind of reverse the model to see that if certain data was part of the model, like if it was part of the model, they should have a high probability of generation or high basically gradient in compared to things that was not part of the training. Model inversion is one that, and that's normally is used to regenerate the training data. It's not a straightforward technique, but it's possible that you can kind of like start giving data to the model, look at the behavior, and basically start generating the data that has a higher probability, higher density, or higher gradients, and using that basically you some sort of like a loop, which again it's only possible if you can make that many API calls also, or if you have access to the model locally for doing something like that. Then you can regenerate the data. And model extraction is when you reverse engineer someone's model. And that's why as part of the model hardening, normally especially if you deploy your model to the edge devices, which that means that your model is sitting on user's machine. You don't want everyone to be able to go open the model and load it, so you need to ensure that there are certain encryption level that you have applied to the model that user basically doesn't have access to it without the key. One of the, let me give you an example. One of the things that we were doing previously in my previous company was, so we were shipping models to customer, and we wanted to be sure that, well, if the model is here, you cannot open it. So if you think about like Intel CPU, I think I don't know which other brands also has this, but I think almost all of them at this point, they have this, the CPUs, they have this region, enclave region, as kind of like it's like a trusted region. And that part of the CPU, it's built for storing sensitive keys and stuff like that. So that means if you are an application and you don't want, because if you are an application and you encrypt it, in reality, what happens is that where are you keeping the encryption key? You need to keep it on the same machine, right? So if the key is also on the same machine, and if there's a good hacker comes, they will also find the key. They search for it and they will find the key. Even if you break it down and stuff like that, they will find it. So the idea that I think they have here is that you write the key here, and whenever your application needs to open, what it does, so application has some sort of like so there's this connection between these two called trust, some sort of like a trust connection. So the application can authenticate itself with that basically physical part of the CPU and says, okay, I'm valid, give me the key. It will give the key only back to the application, and then when it's done, basically the keys disappear. So that's one of the ways that hardware producers and basically companies, when they send the models to the local devices, that can protect it. Otherwise, it's kind of challenging for encryption. The other one is kind of like some sort of like a behavioral harms, and one of the behavioral harms is poisoning, and the other one is evasion. So poisoning is when you purposely add like some sort of like a bad data, fake data, with certain intention as to the training basically data set. So example of that is it'd be so let's say that I think there was this hacker groups that they did something like that for insurances. So what they do is that they poison the data for like a large amount of insurance data for premium cost. Like how much, if you want to get insurance for your car, how much is your premium? So all the data are normal. What they did, they for their own cohort, based on the similarity of the customers, for their own cohort, they reduce the cost, the premium cost by a lot. Everyone else is normal or high, right? So no one gets suspicious. For years, they were having really low premium because that data was being used as part of training. So that becomes the idea of the data poisoning. Another idea of data poisoning, which these days is more common, and actually like I think all these companies that they're using large language models these days or building large language models, one of the steps that they take is to ensure there is no poison data. Because what you do, you go scrap the internet, right? So you have all this data on internet. So one of the things that hackers they do is they create websites. So let's say I create a website, and this website is technically full of Trojan malwares or links, like for phishing and stuff like that. And let's say this website is like a food recipe. So they will write really nice, good, like a food recipes and everything. And at the end, it says that, for example, click to this link to get download the full recipes and stuff like that. And this website, they never bring it up. It's up, but they hide it so it doesn't get the traffic. So because if it gets traffic, they can get reported. So this website has been out there, well-written English, no traffic. And when it goes through the basically web scraping, it comes up, okay, there's nothing against the website name. It's well-written. That data with the link goes to training a language model. And then later someone comes and asks, I want a recipe for this, and that link comes up. And then everyone clicks on it. So that's one of the things that for data poisoning, and a lot of these companies these days, they have ways of trying to detect these types of things because it's common. And then evasion was the idea we just saw that if you know how to deceive the model by adding certain type of noise or data perturbation to change the output of the model. Now, there are a couple of tools that you can use. One of them is called Clever Hands. The other one is called Fullbox. So these are like, at least they were open, basically open libraries. I have worked with this one. The Fullbox is pretty interesting. What it can do is that you load your model and it will create the adversarial attacks. And it makes also like a random attacks to this to your model and provides you a result of like what could go wrong with your model. Clever Hands on the other one, it's kind of like it helps you with some sort of like a benchmarking for your model. So I haven't worked with Clever Hands myself, but Fullbox, it's open source and you can basically use it. Another way of ensuring that your model is not sensitive to adversarial example is what we saw before, that knowledge distillation, the teacher-student basically method. The idea, if you remember, was that you have training data labels, you develop a model with certain temperature, that model produce some probability vectors for the outputs. Instead of using the actual label to train your student model, you use that probability scores to train the student model. So by doing so, your basically model is not sensitive to the actual data and perturbation in the data. So it's a common method to have more basically, to be less sensitive. We use distillation. The other thing is we're going to talk about is residual analysis. So residual analysis is basically focusing on your model, basically prediction and the errors that the model have. Okay, so the first thing about error is, again, randomly distributed error is a good sign. If you're looking at the error of your model, if it's randomly distributed, just random, it's a good sign. If there is some sort of like a correlation or like some sort of systematic error that you can see in the result, that's not a good sign normally. So on the left, it's a good, basically, it's a good model because if you look at the error, it's kind of like a random with respect to points. Here, what you see, there is some sort of like a correlation. That's normally indication of like, you need to improve this model. You can improve it because if the error, think about it from this perspective, that if the error has patterns, you can predict this. So you should be able to improve your model to avoid this, this pattern. All right, so that would be the idea. The other thing is that you need to also, so let's say you did feature engineering and you dropped 100 features, you developed a model. And you test your model, look at the residuals that you have. One good test is that to do a correlation test between the residual and the features that you didn't use in the training. If you find any of your features that you didn't use have a high correlation with the error, that feature should be part of the model because it could improve that. Okay, so that becomes a way to also some sort of probably feature adding. And then adjacent residuals should not be also correlated with each other. So that's you shouldn't have autocorrelation among your basically residual. Are this clear? All right. So the next thing is the model remediation. And model remediation, there's some techniques that we can basically use. Data augmentation is one of those, and the other one, interpretable and explainable ML. Data augmentation, we have talked about this before. The idea is just to add synthetic data for some sort of like adversarial data to help basically your model to, especially for the part of your data that you don't have enough, like, or your model doesn't perform good, basically to add more like a data point for those ones. And normally, remember, you do augmentation only on training data. You don't do for validation or testing. And then the other one is interpretable and explainable ML. First, no longer this is valid that neural networks are black box. It's no longer valid. We can interpret those. But it's also important because if you know how your model works, if your model is interpretable, explainable, then you basically know how your data is transforming across these models. So then there's some also remediation techniques. For example, you can do model editing. If you look at decision tree, that you can apply model editing, pruning the trees and stuff like that, editing. Or you can manually tweak your data based on some business cases that you have. Model assertion, this example of you have a model and your model says accept the loan, but company has a policy that even if the model says accept the loan, based on this, override the rule and reject it. That becomes the model assertion. So you, even though the model says yes, but you have certain policy that you override the results. Right? You can think about model assertion, maybe not exactly, but the guardrail that we put around basically chatbots. Because the chatbot, it just generates text, and then we override it by not allowing it to return the results or not. So then the other thing about the remediation is that, like discrimination remediation, the idea will be that be sure that you include people from different backgrounds. If you're doing data collection, be sure that you do feature selection, use fairness indicators or fairness metrics when you want to select hyperparameters or thresholds to ensure that your model is basically fair. Then you do model monitoring, you do anomaly detection. And again, model monitoring, the idea is that be sure that you monitor your model across time on certain intervals or like continuous, depending on your time case. Inspect for accuracy, fairness, security breaches, or if something is changing in your model. And the anomaly detection, just be sure that you have a way for dealing with anomalies. Especially when it comes to ML, most of the time anomalies are around your data than the model itself, because the data is like a first-class citizen. Data comes through your pipeline, and it triggers certain basically anomalies. And sometimes anomalies could be basically sign of attack. That means people are maybe doing a random attack to the pipeline. And so that's about the anomalies overall. But now the next thing is I just talk about fairness, which it's a topic that's, I think there's a huge disagreement among community on that one. At least I have talked with some, I remember recently I talked with an engineer and when I was like, how do you test your model for fairness? It was like, oh, you're one of those engineers care about explainabilities. I didn't have anything to say. I closed the conversation. I was like, all right, never mind. But be sure that you care about how my model performs and how my model behave and how my model is going to impact someone's life. It should be really important. At some point in the future, you will be also at the end of a model, right? So it's good always to have a good practice with this type of things. But yeah, there are some libraries that you can use for like open source libraries for fairness detection. I think if I'm not wrong, Google has one of the best one. I don't know what's the name of the library. It's like they have open source library for fairness detection, fairness indicator. What it does basically, it has there are a series of metrics. It basically runs that metrics among slices on your data to understand that if these metrics are the same across for everybody. Your model is fair. Not necessarily is fair, but because that actually could be wrong, but because we are not testing for everything. But with respect to the test that you do, your model is fair if it's behaved the same across all the slices, right? So, but that doesn't necessarily mean it's actually fair overall. So now some aspect to consider when you check for fairness. Always establish some context and for different user, different basically scenarios. Ask someone that has a knowledge about what to look for. Especially imagine you go on a data set and it's like a large data set, you don't know where to put the slice. Like which column should I use for slicing, right? That could be a good question that you ask someone with knowledge, domain expert that, hey, if you have this data, what would you basically look for? You know, that becomes pretty useful. Then compute the performance metrics for all those slices, and then just create certain reporting. We're going to just talk about this. Now, when it comes to what to look for when measuring the fairness, first thing is that, well, positive rate and negative rate. So the idea of positive rate is that you want to be sure that everyone at all the groups, they have an equal positive rate, right? Because that basically says that, or equal negative rate. Not exactly equal, but within a certain, basically a standard deviation of each other. Then you can look at the true positive rate, false negative rate. And this is for a scenario, let's say, when you care more about true positive rate, that means that you want to be sure that every group, every basically cohort that you're looking, they all get same admission rate. Like that becomes where the true positive rate becomes important. And then you could care about true negative rate, and you can basically, because think about this. Let's say if you're only looking at the true positive rate and it's the same across all, and you could say that, oh, my model is fair. But then you look at the true negative rate and you see that it's actually has the basically it's disparate compared different groups. So you want, and true negative rate becomes scenario like you want every group to have same rejection rate also, right? So you need to basically compare for both, not just one, because it's not like a one versus the other one. Then accuracy and area of the curve, and these are more like when you care a lot about the precision, and the precision is kind of like out of all of the one that I said through, what percentage are actually basically true. Like it's kind of like a if you always shout wolf, how much should I trust you? You know, it's kind of it's like that. That's the example, a good example for that. Then, just be sure that when you do fairness, it's not one-time test. It should be part of your evaluation and the monitoring pipeline that you have. So we don't need to do this one. All right. Now let's go to continuous evaluation and monitoring. So one thing that's always remember is that the training that data that you have is just a snapshot of the word at that given time, right? So it's just a snapshot. Data changes over time. Model don't age good. Model actually perform worse. And normally when the model performance goes down, that's a warning sign. And you need to always be sure that when you have a monitoring pipeline, you monitor for data drift, concept drift, data shift, and we talked about this before. Concept drift is when the probability of Y is basically changing, or Y given X is basically changing. That means the condition of Y given X is kind of going around. And then you have the covariate and prior shift. You care about the probability of X is changing or probability of X given Y is changing. You basically need to monitor for different distributions. Based on that, have some alert rules. Now, the overall is that during the training, you have certain, and this is what you did in your project, hopefully. You have a schema, a statistic from your training data. And whenever there's a new data comes, the new data goes through prediction pipeline, but also need to be compared with training a statistic and a schema in order to see that if it's the data that we should continue or not. Now, when it comes to monitoring and alert creation, how should I create an alert, and what should I use what methods should I use for that? One of the common one is a statistical process control. And this is a common technique in manufacturing. When you want to find if something is faulty and the pipeline is basically creating more faulty tools or product. So it's statistical process control. What it does, it basically says that the error comes from some sort of like a known distribution. And I think in this case, we say this is a binomial. So we said the error that the model has, comes from some binomial distribution. That means there is a probability for making error. That's kind of like fixed. And so here we say that because it's binomial, so it has a mean, it has a variance. PT is the probability of error at a certain time. So you say that, well, right now our model makes 10% error. So that's the PT, okay? And N is the total data point that you have, so you can find the mean, you can find the variance. You can create an alert rule like this. If the probability of error plus the standard deviation that you have is more than minimum error plus 3 standard deviation, then you create an alert, right? So it's kind of like it's called statistical process control, more common in manufacturing again. And but still you can define the same thing for your ML pipelines. The other one is called like a sequential analysis. This method uses the linear forward rates, and linear forward rates are the same thing that you see here: precision, recall, like a negative positive rate or positive value, negative probability value, and specificity. So here also you can, for each one of these 4, you can use this definition. Here the asterisk stands for whichever you are using. So PT NPV could be here, or P precision could be here. And this term, this technically a normalization. There's an eta, some sort of learning rate for whichever of this that you're using, and 1 minus that learning rate. Similar to a Bernoulli, right? It's like a theta times something plus 1 minus theta times another thing. So that the reason we have this and this to normalize it. So we know this guarantees to sum to 1 normalized probability. So you can define the rule also like this. Then there's another method as like it's kind of like a adaptive windowing. So when you have data that comes like a time series and you want to be sure that this, I can monitor it as like a time series analysis. So in adaptive windowing, you define a time window, let's say 1 hour. And what you want to do is that to compare every adjacent windows together. So you have window one, previous window, and the current window. And mu is like the error rate, let's assume here. And what you are basically saying that if the error of the previous timestamp minus the current timestamp is more than theta of half fitting. So this is kind of like some sort of like a boundaries you can think about it. So if this value is more than this, then you create an alert basically. Okay, so this if you do time series analysis. So all of those that we so far saw, these are basically supervised techniques, right? Because you need to have label. That's why you need. That's how you know the probability of error. Without the label, you technically don't have that. Now, what if we do unsupervised? Like, what if we don't have labels? And then one easy idea is like, well, let's do clusterings, right? So, clustering techniques are pretty useful, especially if you think about this. I have a data and I create these clusters over the training data. It's just one idea. And then new data comes. And as new data comes, I add it to the previous data that you have. And I redo the clustering. If you see there is a shift in the cluster groups as data being added, that is an example of anomaly. That something is basically changing because as you add data, your cluster is changing, shifting. So that could also tell you that there is an emerging concept. There's a new concept comes into play. There are some techniques that you can use, Olinda, Minias, and EC- and so on. But the problem with these techniques is that, well, any clustering techniques, they deal with the curse of dimensionality. The more dimension you have, it's harder it gets, because the reality is that as you add more dimension, the distance between points becomes larger, right? So that becomes a problem. And also, it does not detect population level change because it's cluster. It's kind of like a local change across your data. So it just tells you that if this point with respect to the point around it is different, not with respect to every other point technically, right? So another way that you can do is kind of like a feature distribution monitoring, and that's what we talked before. If you build series of distribution around your columns or features that you have in your training data, and you compare that when the new data comes, you compare it against that statistics. You can do a Pearson correlation for comparison. There's a Hellinger distance, basically, you can use also. And then if you have a higher dimension, you can apply PCA first to reduce the dimension. But this is also one way, it's like more statistical. Question? Right. So the other one is that kind of like a marginal density approach. And this is the one that I think I have said a couple of times in the class that when just think about the example of a binary classification. And there's a region here, it's kind of like a region that you show your model is uncertain, like a binary, like the probability is between, I don't know, 0.4 and 0.6, for example. And during the training and validation, you have a sense that only 10%, like I don't know, 10% data fail in this region. That's the idea you have. And that normally, again, this is the region that the model, if it's a binary classification, and sigmoid tells you, I don't know, it just gives you always something close to 0.5. Now, during the testing, if you notice that your model start producing lots of values in this region, more than that, the 10%, but you start every time you see your model result, it falls in this region of uncertainty, multi-class or binary, have a frequency count, and you like convert it to a probability. And if it surpasses what you expect, that means you have change, or your model is decaying. So some sort of like either the data is changing, there's a change in your data, or your model performance is going down, and so on. So you can use that as a way to create an alert. All right. Okay, so that's it. It's just an example of Google Cloud has this. So if you work with your Vertex AI, I think for those of you who do Vertex AI, if you do deployment, it gives you the option for monitoring and drift detection and stuff like that. All right, if you are deploying on vertex, right? So I think you have that option out of the box to use. All right. So the next part of the lecture, we're going to first talk about interpretability and explainability of the models. So, but let's just start with definition of responsible AI. We all can agree that AI is basically need to be used to enhance people's life, right? So no one disagree with that. We need to use AI as much as we can, as much as we don't harm technically. And that means that, well, the idea of responsible AI, and responsible AI means that, well, whatever you build, it should be fair for everyone. It should be explainable. It should basically adhere to the privacy and security concerns, right? So that should be a motto for you when you build that. Now, explainable artificial intelligence, or XAI, right now, which is a field basically, and the idea is that be sure that types of model that you are using are basically kind of like they have algorithmic fairness. Right? There's certain models by default, by nature, they are not fair. It's kind of like and they're like hard to even interpret. Be sure that you identify potential biases in your data before developing, because otherwise, if your data has a bias by nature, it will transfer to your model. And at the end, to be sure that your model works the way that you're hoping for. So whatever model that you're building, you need to be sure that it's basically it's work fine. It's basically strong against attack. It's fair. Otherwise, it will harm your reputation or basically branding. You need to be sure that you adhere to regulatory and basically legal concerns. And basically, at the end, again, whatever you build, you need to be able to answer to customers and stakeholders. And this is, again, another example of that you can fool like a deep neural networks. So this is an image that the model should predict really good. So clean image model says this is a washer. And here we add adversarial version, certain level of noise. And the model said this is a safe. You add increase the noise. Basically, now it's no longer a washer anymore. It's like a safe or loudspeaker, right? So just example for you that these types of model can easily be manipulated, and we need to be sure that we know that, and when we build it, we test it against this, or you add certain basically techniques during the training, so that makes your model basically more robust to perturbation in the data. And this is another example. These are like all these papers are out there. That's a pandas. If you add this noise, and now this is a gibbon. It's like and model is pretty confident. On itself, on the panda wasn't confident, but now it's like 100%. It's like I'm sure of it. So now the next thing is we're going to talk about the model interpretation. So the first thing is that, well, and this is the same thing that I talked with that person. I was like, you need to be able, if I tell you why this model basically said yes, you need to be able to trace it back, especially for certain models, especially if it's not a deep neural network. You need to be able to answer it. You need to basically answer why the model behaves in certain ways. And can I trust this result that the model gives me? Otherwise, how do you trust it actually? And then what information basically you can get from the model. What the model can provide you also. This is already important. Now, when it comes to model interpretation, there are a couple of techniques that we can refer to, or basically types. You can look at intrinsic or post hoc techniques. We're going to talk about those. It's going to be model specific or model agnostic techniques, and it's going to be local or global techniques. So these are all pretty useful, and I think today class, I think is something that you can benefit definitely in your career, because it's not just as MLOps, it's just for any modeling, ML modeling that you do, you can basically use these techniques. Now, when it comes to intrinsic or post hoc and overall, we have certain models that are intrinsically basically interpretable. They're the models that they're interpretable by nature. And those are like linear models, tree-based, lattice, and those are like by nature are interpretable, right? And post hoc methods, on the other end, it doesn't care about how the model works internally. It's just a black box evaluation. And it's agnostic to model architect. It does just think about the post hoc is just a pipeline that you put any model in it and it basically evaluates it for you. It extracts relationship between features and the model prediction, and you apply it after the training. Okay, so that's about the post hoc. Types of summary or results that you can get back from these models could be features, summary statistics. And that's overall like how the features are correlated maybe with respect to models output and stuff like that. Features, summary, visualization, model internals, how it works, and data points, like what happens if you change a data point by a certain value, will it impact the model's output or not? So I give you a series of summaries, this post hoc methods. And then the other one is like a model specific or agnostic. Model specifics are the types of tools that basically bespoke for your model. It won't apply to other models. It's just you built it for your own model because you have a custom basically made model. And the model agnostic on their end just doesn't matter which model is that. It's like a library you imported and you can apply it to any model that you are basically working for the certain types of data. So model agnostic versus model specific. And you can look at all of those like something like this. Model agnostic, model specific, global, local, when it comes to basically interpretability of these models. And now the understanding is to understand what's a local versus global. Local is when you try to interpret your model's behavior with respect to a data point. Global is when you try to interpret the model behavior with respect to all the data. Okay, how my model works with respect to one data point. This is here an example of we pick one data point to the model, and the output of the model, basically blue means lower and red means higher, depending on the value. Now these are the column values. Basically tells you that how each features impacts the result of the model for that data point. That becomes local. And global on the other end basically becomes across all your features. And this is like a SHAP value. And we're going to talk about it if you don't know it. And it just provides you a summary across all the columns that you have. So what you see here in the SHAP value here, on the color base is like the feature value. If the feature value is high or low, and there's a SHAP value, the impact of that feature on the basically on the model output. If what you see, if the feature value is high, it's basically could be to the left, impact on the model, negative, or could be positive. And when you have something like this SHAP value, and again, we're going to talk about it more, you're hoping if you build a SHAP value over your data or your model, to see this some sort of like a distribution among your columns. That means you will always have series of columns that they don't have any SHAP. These are the columns that are not important. And you will have some columns that have a really wide basically distribution. The thing that you don't want is to, when you're looking at this SHAP value, let's say you have 100 columns and you see 3 of those, they have values, 97 of those almost, they don't do anything. That's could be an identification of like an overfitting. You want to be sure that your model is using every column to a certain level, but you always have some columns that they have SHAP of almost 0. Now, intrinsically interpretable models. Let's talk about those ones. The thing about intrinsic models are that, well, this model is like a linear model. It's like a straightforward, you know how it works, like a tree model. It's, you can look at it even without the knowledge, you can understand what basically is going on. Like I said, the model nature itself basically interpretable. Like it's not like a neural network that we assume is like a black box because it's just not intrinsic by default. One thing about functions or models, in order to be intrinsic, they need to be monotonic. Blue line is a monotonic, green is monotonic, red is not monotonic. Monotonic function is a function that doesn't matter what data you pass, if the data is increasing, if the value of data is increasing, the model's output is either always increase or decrease. It doesn't have a change. Okay, that means if you increase the amount of rain, I don't know, like the water level always goes up. It's not goes up and sometimes goes down. It always should be in one direction. That becomes a monotonic model. If you think about the regressions, are monotonic. When it's like the way that the formula is, right? So just when you increase features, it always either goes up or it goes down. Now, this is just a good table for that. So regression, linear, monotonic, there's no feature interaction. Logistic regression, non-linear, monotonic. Decision tree, non-linear, is not monotonic. No. Rule fits are not. K-nearest neighbors is not. And then there's this, I don't know if you ever heard of TF lattice, TensorFlow lattice. It's a type of model by Google that's pretty linear and monotonic and interpretable. You can always have this idea of interpretability versus accuracy. You can always look at it this way. The more complex models get, and this, as you can see, the complexity of models also, the higher the accuracy, the lower the interpretability, right? So decision tree, linear regression, stuff like that, they are more simplistic models. They're easily interpretable. As you go down toward the neural network, that interpretability drops and the model accuracy goes up. But this one library or this one types of model by Google, Lattice, has a really high accuracy, but it's pretty interpretable. Okay, this is just a linear regression. And it's just summary of why linear regression is interpretable, which makes sense. If you perturb a feature, or if you have, for example, what it says here, if I have a one-hot encoding, if the feature is 1, the value should go up or down depending on the weight it has. It's always the same thing. So it's all right. No, it's just I'm not going to go over this, but this is the basically TensorFlow lattice or TF lattice. What it does technically, so this is Y, the prediction, and this is the 2 columns that you have, X1 and X2. Let's see, we don't have X2, so we have X, Y. So I think that should be for lattice value. So what it does, it fits that, basically that's the lattice that you see over there, or that feature space. And in order to make a prediction, it moves the data along this lattice. So it's like I use it for prediction. It's interpretable, but we don't want to go in it. Why? But I highly recommend you, if you're interested, just import the library and just read the paper maybe. This is just example of what, like how strong is this model. So on top left, you have ground truth, the distribution. So this is the ground truth distribution. And if you apply XGBoost, this is what you get. If you apply deep neural network, this is what you get. If you apply TF lattice, almost identical to the original data, right? So it's pretty strong for learning of data. Now, okay, so let's pass this one. Now let's go to model agnostic methods. And again, model agnostic means that, well, it doesn't matter what's the model that you're trying to test. You want to be sure that the methods that you're using, you basically have model flexibilities. It can explain, it has some sort of like explanation flexibilities, and it also representation. Okay, so it's just you want certain basically methods that you're using. These are the common ones that you can use model agnostic for interpretation. Partial dependence plot, PDP, accumulated local effort, permutation, feature importance, local surrogate, Lime, SHAP, individual plot, Shapley, global surrogate, and stuff like that. So there are more than that, but these are the common ones that you can use for kind of like interpret your model. We start with the PDP. And again, PDP is just, let's say you have 10 columns. And what you want to do is that you want to see that what's the effect of one or two columns. If you keep the rest fixed, what's the effect of these one or two columns in compared to the other ones for the model's output? So what it does, it basically calculates something like this. Across your data point, it calculates some average. XS is, S here stands for the column that you have sampled. So let's say I want to look at column 1, XS becomes column 1, and XC becomes the rest of the columns that I have. And I stands for your data points. So you have this function that it compares the impact of that one column and compared to the rest of the columns. You can do up to 2. So XS doesn't need to be only one column. You could look at the impact of 2 columns versus the other one. But that also becomes the challenge that this technique has, and is you cannot do it more than 2 columns. So if you have lots of columns, you actually need to keep basically doing a combination of 2 versus every other one. So it becomes hard to read the result. And this is one thing that you can get from PDP is if this is for the bike prediction number of bike and temperature, so it tells you if there is a certain patterns in that for that column. So this, if it's categorical, also it can give you something like this. Advantage, computation is intuitive, easy to interpret, easy to basically write. Disadvantage, as I said, that you can only do 2 versus all. You cannot do more than that. So it becomes challenging if you have too many data points. The other one is a permutation feature importance. And this is like a really interesting technique is that, imagine you have a series of features and you want to see if they're important. If I pick one column and I shuffle it around randomly, just one column, keep all the columns fixed, what will happen on my model's output? So imagine you have trained this model and I go on a column which is height and I shuffle the value of height across all the rows. Look at the error that you're getting. If the error increases, that means that that column is pretty strong. Your model needs that column to be always there. If the error is just doesn't change much with that column basically permutation or basically randomness, then that's not an important column. So that becomes a permutation feature importance. It's an easy way for you to see which columns are more important. Just randomly shuffle the values one at a time and see the impact on the error that you have or the accuracy that you have. So again, the benefit is that they're like easy to calculate. It provides you with some global idea. Doesn't need for you to retrain the model because you have a model. You just basically change the data. The disadvantage is that, well, the first thing is that we actually don't know if it should be on the training data or test data that you need to use it. It's not clear. And then you need to have a label. That's itself is a really challenging use. So the other one is called Shapley value. Now, Shapley value, it's technically comes from the like a game theory, it's the idea of Shapley value. And the idea is that if you think about certain players that you have played together, and at the end of the game, everyone wins, like the group wins together. Basically, Shapley value says everyone won, but not everyone contributed the same. So the idea is that who contributed the most toward winning, that player need to receive more credit. And if the idea like your project, who put most effort into your project, that person gets a higher score. I'm just kidding on that, but now everyone is going to start creating commit on the GitHub. So, but that's the overall of the Shapley, and the Shapley, it's the value that it tells. It calls payout. How much that person or basically the player should receive as a payout. Now, let's look at the example of Shapley. So let's say you have this app that produces the price of the house. You make a prediction regression. There's a park near the apartment. This is the apartment size. This is a second floor. You cannot have a cat, and the app predicts 300,000. And then you're looking at let's say one bedroom. Let's assume is one bedroom. You look at the similar one bedroom houses, and you see that on average it should be 310,000. On average, one bedroom in that region. And the question is that, well, why the model says 300? Where is this discrepancy comes from? Right, so you need to be able to justify that. And the idea of basically Shapley value or the game theory, you can connect it is like this. The gain here is that you wanted to predict the price of the house. What is the gain? The gain is -10, because the gap between that becomes the gain. You basically lost -10,000 for selling the house. And what are the players? And the players become the features that you are used the model used in order to make that prediction. So, and this is just a random result. It's not the actual result, right? But one possible explanation could be that, well, because it has a cat band and just there's a negative cost, like people didn't like it, and that led to basically having total like -10,000 differences, which could be one possible scenario. But that's the idea in the Shapley value. You try to look at the problem. What was the gain as a positive or negative? What are the factors or the players? And try to understand which factor contributed the most toward that gain that you have, either negative or positive. So the advantage are that, well, it has a solid theoretical basically formulation. It's fairly distributed. It gives you some options to have contrasting explanation. It has more disadvantage than advantage. It's computationally expensive. It's hard to interpret because, as you see, the one scenario was that for that one house, we could come up with series of scenarios. You could easily misinterpret the result. You cannot use it for something like a what if I change this? It doesn't give you that option. It's not a predictive model to understand that if you change something, will it increase the result or not? And then does not work well if the features are correlated. So this Shapley value basically had these problems, and that's where the recent changes came with SHAP, or Shapley additive explanation, and this becomes more popular to use instead of Shapley value itself. Now, the SHAP framework, basically the way that it works is that these are like a couple of extension for it: tree explainer, diff explainer, gradient explainer. If you heard those terms, those like functions or libraries, those are basically idea of SHAP. So this becomes example of SHAP. So it's just like it predicts the value as some sort of like forces. So those are like called force. The forces are either negative or positive. So impact of a column on the model output is a force, and it's like a positive or negative. you start always from some average prediction as a baseline and try to see that if you add feature, which direction it will basically pull you. So that's, again, this is just for one example. And then if you go to across all your columns and across all your data point, this becomes the SHAP value, right? And just remember again, SHAP value tells you that the importance of a column over across all your data point in your data compared to your model prediction. If it's distributed, that's a good sign. If it's like this, that's not a good sign. So this is not technically a good sign, because like you see, everything is almost zero. They have a couple of points, but the top two, they have the highest variance, because it could be some sort of like overfitting. Yes.
Are each of those points like one data point?
Yes, so it will be one data point. Yes. So you should technically have, so here you have overlap, that's why we don't technically see it, but you have same data points here. So this become another way of looking at the Shapley for one column. So here we have the temperature and we have hour, and the value is basically changing like that. So the color coding, it tells you about the temperature, if the temperature is hot, the temperature is cold. And what you can see here is that there is a pattern. So this goes up and then it goes down and it goes up and it goes down and it goes up, right? You can basically connect these points and create some sort of like a pattern. And that pattern should be able to be justified by hour, because this is for, I think this is, if I'm not wrong, it's for the bike ride. And then there's a temperature and there's a bike. No, I think this is just an hour and temperature, maybe. So it makes sense that in at midnight, it's kind of like a cold, then it goes up, or no. I don't know what's the exact data set, yeah. Maybe not. Oh, this should be the bike ride, but hour and temperature, yeah. Doesn't say, okay. Anyway, so that becomes the SHAP value, but you should be able to find a patterns on like some sort of an increase, decrease based on the increase and decrease in the column value. So now the next thing, testing concept activation vector. And then this is the concept activation vectors, especially for neural network internal states, like if you want to interpret those types of models. You can look at this one. For example, on the left, what you see, have you all heard about the definition of concepts? Like if you think about the, let's say I have an idea, like I have a dream, I had a dream, and then I don't know, I saw a dream of a car, and I woke up and I want to talk about this dream. So I can talk it, I can draw a car, I can write down a car in different languages. The idea, the concept is the car, and there are different ways that you can present it, right? So, and that's why if you think about these generative models, multi-models, idea is that we have a same concept, we have different modality that you want to show it. We want to basically be sure that all of those, they can map to the same thing. That's the idea. Now here, if you think about the image, and let's ignore this image for a second. Let's look at the image, think about the image of faces. You have an image of all just like faces, and you want to learn. And if you think about the concepts that your model can learn, could be concept of smiling, concept of someone is basically like a, I don't know, like angry face, like a blue eye, brown hair, and stuff like that. Those are all could become a concept that you can learn. Now here, this concept becomes, says the concept of the CEO, and during the training, the model has learned that any time I saw a picture of CEO, they have this stripe, like a shirts that they are wearing, not mine, but they have this striped shirts. And the least similar concept for CEO, this is what the model predicted. Now you can ask the same question. So here says that for model woman concept for the tie, that's what the model learned, and the least similar one, this is what the model learned. So that becomes the idea of concept, and that's, if you think about it, that's how you can ask a question from a model that return me a data about, I don't know, like a model woman. And if understands the concept, it should be able to query against that to return it for you. Without understanding the concept, the model only basically does a discrete search, like an exact search. So that's why we basically, at this stage, we're really good at searching and retrieval, because actually all of you doing RAG probably in your project. So that's the whole idea, right? So you pick the data, learn a concept over some sort of like embedding, and you basically retrieve that. All right, so you should be able to answer a question with respect to that embedding. Now, the next one is LIME, and LIME stands for Local Interpretable Model Agnostic Explanation. It's like a long name, but it's a basically local surrogate model. So think about this. I have a model is expensive, and it's hard to interpret, but it's good. The idea of LIME is that I don't want to get rid of this model. I will develop like a less expensive model, but interpretable model as a surrogate for interpreting the result of the other one. So you have the good model, you bring a smaller model to train with respect to good model, and you use those one as a way to interpret why the result of this one was like this. So that's the idea behind LIME. Does that make sense? Okay, so the last thing is AI explanation. It's just we're going to pass, but if you're working on with Vertex AI, you have these options to use series of out of the box tools for interpretability over your model or what you're using. Okay, let me see. Yeah, so on this one, these are like all on GCP. All right, let's stop here, take a break. All right. So here, what you do, you start just going to the Kubernetes engine. And when you're here on the left, you see clusters. And here you basically say create. When you do create, by default, I think these days GCP is on more like an advanced version of like it's called autopilot clusters. Change it to the standard cluster, you have more control over it. So I switched to a standard. So what you need to do is that you need to provide a name, select the region, similar to what you did with VM. Name where you want to serve is local or regional, and leave, so this is the target version. Basically, you can just, for the Kubernetes version, so just leave it the default. Then you need to go on the left side. So first thing you see on the left says fleet registration. Now, fleet registration is when you have multiple clusters, not one cluster. You have a series of clusters and you want to group those together. You use a concept called fleet. We don't have that here. We just have one cluster, so I don't need to do that. So I pass that and I go under that says node pools. So you start with the default pool. You can change the name if you want or something, but just leave it to be. Now, the first question has that how many nodes do you want for this cluster? By default is on 3. On the right, if I zoom out, you will see the cost of the cluster. When you change the numbers, the cost basically changes. Okay, so just keep in mind when you try to deploy yours, maybe get some sense of how many nodes do I need, how many pods do I need, and stuff like that, instead of just generally have multiples. So then you have this basically like an update concept. It tells you that if there's an update to the node and I want to update it, how should I update it? Should I basically kind of like update it all, or should I do green update? So we can just leave it to be. That's overall updates for the nodes. It's not something you need to worry about, at least at the moment. That's a default node. Now, inside of the node, you need to define about pods and also the definition of the node, like how much compute power do you want on this node? So you go under the default pool, you go to the nodes, and the first thing that you see is image type. It basically asks you that what type of image do you want on this machine? You can leave it on the containerized OS by default, or you can select Ubuntu, just depending on what you need. Then it goes down here, and this is the same thing that you saw in the VM compute engine. Select the VM machine that you want, maybe medium, micro, or what you need. When you do that, the price changes again. Okay. Then same thing that we saw in the previous lab. How much space do you need on it? Like how much gigabyte do you need? That's it. If there's any networking, we can also decide maximum pods per node. If there's a network tag you want to add to it, we don't need those. Security we don't need. Metadata we don't need. These are just by default. I say we don't need it. In real life, probably you need that. So then you can just say create, or you can get the command line and do that. So I'm going to use the command line to make this easier. So I basically have copied the same code here. So every time I want it, I don't need to go through the whole process. And you just basically run this on your machine. So yeah, so this will create a Kubernetes. So now you will see if I refresh this, the thing about Kubernetes is that it takes time to come up. So this right now is being created. Whenever that's complete, then you can access it. It says number of nodes 1, and that's the default. So if you go also on it, then it tells you what percentage is completed, 31%, for example. Now, after this is done, let's go back to So in order to access the Kubernetes on your machine, you need to do gcloud init first to be sure that you authenticate with GCP. Select the project that you are accessing. So be sure that the region for that authentication and the region that the cluster is the same on your machine. That's it also written here. Then what you want to do is that you can run something like gcloud container cluster get credential, the cluster name and the zone. And we will see that you can find it also here. So when this comes up, still running. So if I say connect here, you see this code that gives you for connection? That's the same code that we saw over there. gcloud container cluster get credential, name of the cluster, the region, name of the project. So you run this one time in your environment. This is 64%. And it's still here also says it's continuing. So you run it one time, and then you can basically connect to, like, use kubectl over there. So let's go back here. Now, what we have left here for you, what we have left here is list of commands that you can use for kubectl to access and to manage things on your Kubernetes. I'm going to talk about some of those, but overall is that your first step is to build a cluster and be sure that via kubectl you can access that cluster. Okay, so that becomes the first step. And I need to do that after this is done. Then there's a second basically lab. In the second lab, we are going to talk about how we can deploy something to this cluster. So I have a cluster and I have an app. How can I deploy that app to the cluster? And how can I be sure that it's being served? Okay, so that becomes the second one. Now, because we are using this kubectl, what we're going to focus on is, so let's say you have this Docker file, and this Docker file is simply nothing. So let me go to the main file first. There's a main Python file which imports a fast API, and it simply just creates a root, which if you go to it, it should say hello. Okay, so this is the app. Now, we containerize this into a Docker file that simply using UV-kern will serve that app. One thing that you will see is that this basically UV-kern, it exposes port 8080. Okay, so this containerized app will serve that application on port 8080. Okay, now we want to serve it. We want to deploy it and serve it. So what you see in this folder, the Kubernetes folder, it's called manifests. So when you work with Kubernetes and you basically you need these YAML files that are called manifests, and the manifests basically are the state of things, how things should be done. It's kind of like a blueprint technically. So you need certain manifests. The first one that you need always is a namespace. A namespace is the same thing I just told you, that you need namespace to group, to separate things from each other. So the first thing you want to in namespace is that I'm trying to run an app. What's the namespace this app should run within? That's basically the layman term. So you create this YAML file namespace, and similar to probably what you saw in your like a Git actions. So API version, you give it a version. What is the kind is going to be namespace. Now, where should I get this kind? I have provided a list of all possible kinds that Kubernetes and kubectl has. But it's like it's not a random name. Its namespace is default. It's like a known name. So kind is a namespace. Next thing you need is called metadata. For namespace, the only metadata you need is name. What is the name of this namespace? So it's a namespace and it's called MLOPs. Okay, so this means that this is going to run in MLOps namespace. Now, so we need two other things. One is deployment, which becomes the idea of like deploying the app that you have. One is becomes service, and service becomes the idea of serving it technically. So let's just start with the deployment. Now, it starts on, zoom in. One less. So it starts here, same thing, what's the API version? What is kind is going to be deployment. It always need that API version, kind, metadata. And here the metadata that you need, it becomes two things. One is we are deploying something, which namespace this belongs to. So every time you want to do that group by, so you need to say, specify the namespace. Then what is the name of this deployment? Here we call it fast API app, for example. Then, because you deploy this, it tells you that, okay, what are the specs that you need? You're deploying something. So here what we say is that we need two replica. Okay, when we deploy this app, we need two replicas of it. And then basically it tells you that when you try to create a replica, it doesn't know what replica of what. What we tell is that to select the replica if the label matches this app. So it looks across the app that you have, says, okay, the one that matches Fast API app, I will create two replicas of that. Then basically we see that there's a template for that replica creation. So we need the metadata label. It's going to be app fast. There's a name for it, Fast API app. What's the spec do we need for this? So a spec here is that we are deploying an app. Where is this app coming from? That's the idea. So this app is a container. This container has the following name. This container image exists on this public address or private address, wherever your Docker is. Image pull policy always, that means always pull the image. Don't basically always be sure that you pull the latest. And port, what is the port that this container is exposing? Remember in the Docker was 8080? So you need to specify that. These are become the spec of the application that you are trying to using Kubernetes to create replica over. Okay. Is that clear? So this is the called basically the deployment. Then you go to service, and this is again the place that we are going to serve this. So API version kind is service, metadata namespace, and you give it a name for the service itself. Then for the spec selector, same thing. It should be a Fast API app that I want to serve it. And here, because this is service is responsible for actually making it accessible, what we want to do is that, so our container, which we are putting it on a pod, exposing port 8080. We don't want to let user to access port 8080. We want to do HTTP. So what you do is that you say that I want the port to be HTTP and port 80. So container is on port 8080, but we push it to port 80 for user to access it. Okay, that's the difference. And then we define there's a type for it. So this service, it becomes type load balancer. Remember in the VM, the load balancer was responsible for distributing the traffic. So that becomes the idea. So the service exposes a port 80, and it's the load balancer. So when the request comes, its job is to connect to the deployment, basically where is the pod that's serving. When the traffic goes up, remember we had up to 2 replicas, so it basically can pass to the next replica or basically create another one in case one died. Now we want, in order to scale up or down, what we do, we are going to add some sort of like a horizontal or vertical scaling. Is that clear so far? Any question? It's just laughing.
How do we direct, like, you have 2 replicas, right?
Yeah.
So, like, both can't be accessed using the same.
No, so that actually, first, that's a great question. So we have 2 replica, one of them is being served. One of them is in order to other one die, because we haven't added scaling yet. But if you remember in when we're going over the concept of pods, they have IP addresses. So the load balancer will be responsible for distribution. You don't, as a user, you don't need to know that. Right? Every pod where they save the container, they're all serving on 8080, and they're all being exposed to port 80. So it's going to be the node itself. So the way that it works, you have a node. Node will have a general IP address that will be exposed for user to access. Okay, that public one. Inside the node, you have pods. Pods will run that app for you. When the traffic comes, different pods can access that traffic. But there's only one IP for node that user access. Depending on how much traffic, different pods basically answer. User doesn't notice because user always exposed to port 80. So all of these pods from 8080 will answer to 80 on the same public IP. So it's kind of like become shared across spots. So, okay, so now what I will do, so this one is done. Okay, so that's good. So this says it's created. So if I go back here, this Kubernetes cluster is created. So if I go to nodes, it tells me that there is a default pool, and if I go to workload, there's nothing. So go back here. It's pretty slow here always. Number of nodes, 1. So we have total of 1 node. So if I want to connect to this, again, we click this, copy. We go here. Okay. Now, if I do kubectl get ns, and there's a comments, all those comments were over there. NS stands for namespace. I'm saying that give me all the namespaces in that Kubernetes machine that I just connected to. And what you will see here are, these are the default namespaces. So Kubernetes, when it comes up, it has all the services that are running in order to serve it, like make it possible. And we haven't published anything. We haven't deployed anything. So, kubectl get ns, you can get that. What I want to do is that I want to create a new namespace. So I will basically say that kubectl create namespace MLOPs. And it says that namespace created. Now, if I say this, you will see MLOPs on the bottom. So now I will use the Kubens, MLOPs. Now it's activated the MLOps namespace. Now every kubectl command that I basically type, it will be within the MLOps. So namespace. So if I just say kubectl get, not that one, get service. It says there is nothing because we haven't served anything. If I say kubectl get deployment, this is nothing. What else we do? Get cluster. We don't have a good cluster. Anyway, so now let's go to left. So I'm not going to go lab 1 or 4 anymore. Just go directly to class lab. So in the lab, there are a couple of goals that we have. First was to create a basically cluster, connect to the clusters. Next, what we want to do is so we have, let's assume this is our cluster. So we have a cluster. Then we have one app, and that app is basically a calculator. When you go on it, we will see it shows a couple of numbers. You can sum 2 numbers. It just does the summation. So what we want is 2 things. We need a backend, and we need a front end. Okay. And the way that I want it to work is that user only being able to access the front end. User doesn't know about backend. Front end gets a query from user, and it's connected to our backend via an IP. Then the front end basically passes the query here, gets backend is responsible for running the actual app. Okay? So it basically generates a result, and front end is going to show them. So in order to do that, what we need is so we need some like an image. We need one image here because they're both going to be containerized, 2 separate containers. One is for the front end app, one is for the back end. Okay, so we're going to look at the images to see what's in it. So let's just start with the backend. So there is a main file. Now, in the main file, the only thing you see is a fast API. And then we are using this course middleware, basically. What this does is when you build an app and you're adding this middleware to it, it allows basically, you know, when you write a query, request could have, for example, like addresses. Requests could have these headers, stuff like that. And what we want to do is that we don't want to deal with any problem for this example. We are saying that doesn't matter what's the address, doesn't matter what's the header, doesn't matter what's the origin, just basically use an answer to anything. So here, basically what I'm saying is that I'm adding this middleware and allow any origin, allow any method, allow any headers. Okay, just for simplicity. Then we create this function add that gets two inputs, okay, as a query from the user, and it just returns the summation of those two. And here it just returns the sum of two. That's the app itself. Now, so closing that, then we have this Docker file which does the same thing. It's just using UVcorn, serve the app, expose port 8080. Okay, so that's the backend. That's similar to what you saw before. Now, for the backend, we need to have certain things. So we need a deployment. Backend need to be deployed. And these are the manifests. And we need a service because backend need to also insert. So we need a deployment and a service manifest for backend. Then let's just start here. Let's go to the deployment. I didn't define the namespace because the namespace will be defined across the whole project later in different folder, what I mean. So inside the manifest for deployment, so what you see over there is that there's an API version, metadata, basically the namespace name, a spec. I add 3 replicas, match and it should be only be a replica as backend app. Okay. The template also becomes the same thing for backend app. Now, what is the spec? So this container image comes from this address. That's just address to the wherever is the Docker image. We will pull it. The port is 8080. Now, one thing new you are going to see here, and it's this last part. So here, what we do, we are basically saying that for this image, I need to request certain amount of CPU and memory. So you are for this image, the resource requirement, you are requesting resource to have this much memory, this much CPU. Okay. Now this is MI and M is not megabyte and it's actually mebyte. That's MI, which is more than megabyte, and M is technically a fracture of CPU. So it's like I think that's like a 0.05 CPU. And then, so that's how much we're requesting, and we put a limit on it. And the limit is when that, if you hit the limit, you want to bring up the replica or change the path. So basically you say that the limit is this much memory usage and this much CPU usage. Right? Okay, so that becomes your limit. Any question on that? No? All right, so this is the deployment. Then let's go to service. And the service is pretty similar, just changing the name, called backend app service, backend app, HTTP. So we get 8080, we convert it to HTTP port 80, and the type is going to be load balancer. Okay, so this is just a straightforward, simple backend service. or overall like a service on Kubernetes, just normally look like this. So, okay, so this is the backend. We have a Docker file, and that's it. Let's go to front end now. Now, on the front end, on the other end, there's no Python code, nothing. It's just what we have built here is just an HTML that we are going to serve it. Then it gets user query, and we want that HTML to gets the user query. So this one has the HTML. It will get the query, and we want this to be connected to the backend via public IP that the backend has. Pass the query to backend. Backend has the Python app for calculation, gets the result and return it. Okay. So inside this Docker file, this is kind of like an official image. It's just downloaded for Nginx, and just it's like I'm trying to serve a HTML, so without anything else. It basically copies series of files from this folder into the Docker, and then basically started serving it exposing it on port 80. Remember, the container is the backend is port 8080. We are here exposing only port 80. So front end expose different port in compared to the backend. Okay. Now here, this favicon ICO isn't just an empty file. I just need it in order to make it valid. It doesn't have anything in it. This one, Nginx, this is also like a typical template. But what we are basically saying that this is going to be HTTP server. It listens on port 80. Is localhost. It's going to be this using these addresses, location of the favicon, and basically ignore if anything around favicon happened because it's empty. So this is just a template from Nginx. So it's not like something that I wrote. And then we have this index, and index is again it's just a straightforward HTML. It just opens up, has some colors, and has two buttons for you to select pass two numbers as a query. So here, sum of the calculator. So there is a bottom here that says number 1 is a placeholder. So user enters a number. There's a second one, and there's a button basically that user says it says get sum. User clicks on it. Now, when this get sum is being called, this get sum is a function. It needs to get that query, pass it to the backend, get the answer, return it to the user. And this is defined here. So this is that function, get sum. So what does this get sum do? It basically gets those two numbers from the user query as a constant number 1, constant number 2. This needs to change. This is the IP to the backend. It's because I haven't deployed anything. This is the previous IP. When I deploy my backend IP is different. So you need to actually change this to your current backend number IP address. So this basically what it does. It calls to this address. Remember, backend was a fast API /add. It gets two inputs. Number 1, number 2, and it will return answer, summation of those two. And then we basically return that, it gets it as a JSON, and then we show it. And the rest of it is just to catch error if there's an error happening. So that's it. Again, it's just a simple HTML with some colors, two buttons. Whenever it gets user query, calls to a function called getSum. That getSum calls to the backend IP, public IP at risk, which we need to update it, gets the result, show it to the user on the website. So now, similar to the backend, we need basically manifest. So we need to do the same thing technically. We need a deployment, and we need service for the front end. Okay, so you need the backend and you need the front end for both of those. So you go to front end deployment. Similar, everything The only difference is that anywhere there was a backend, I change it to front end. The image is also different. We have a different front end image. Okay, so everything else about it is different, is the same. Then go here to the front end service, exactly the same, just anywhere there was a backend, change it to front. The replica basically of each other. So that's the backend and that's the front end. Then we're going to, so here inside the Kubernetes, there's a namespace. So that's the namespace file, the manifest. That's it. Then we have two new things. Okay. One of them is written HPA. And what is HPA? HPA stands for horizontal pod scaling. Okay, so if I go here to application scaling, we're going to talk about this later in the class another day, but I'm going to just quickly go over it. This is our HPA, horizontal pod scaling. You have one pod and you have an increase in the request demand. What you do, you replicate that pod, create a replication of the same pod in order to quickly respond to demands. Anytime you scale using same replica, identical, recreate more, it becomes horizontal scaling. Anytime you do reverse, that means you don't have image. I don't think we have image. So the other one is vertical scaling. So vertical scaling is the idea like, instead of creating replica of this, you need to go change it and rent a larger machine. So you have high traffic and your CPU utilization is high. Instead of creating a replica, you increase the amount of memory. You increase the amount of CPU, like vertically versus horizontally. So horizontally, you rent to return. The other one, you just, same machine, you just sell it and buy a larger machine. That's the idea. Okay. So horizontal is more common because it's like you can create a replica when there's no traffic, just get rid of it. So, so here, if we go back to our case, for the horizontal pod scaling, we also need to add a manifest. One for the front and one for the back end, because both of them, they could receive lots of traffic. So start with the back end. And what you will see is that, well, API version, it's called auto scaling version 2. That's by default for the Kubernetes. I think there are more than version 2 at this point. I don't know. Kind horizontal pod auto scaler. Remember again, if you want to know where you get that kind, if you go to the README, there are a list of all possible kinds written over there for you to select from. Metadata, give it a name and the namespace it connects to. A spec. Now, a spec here is that in basically pod scaling, you need to, a spec becomes like what you want to scale, how do you want to scale? That's the idea. So target reference is that, well, we are targeting this backend app. This is a kind deployment, okay? And we are targeting that backend app. Minimum replica 3, maximum replica becomes 10 of that. Remember, backend and frontend, both they had a deployment manifest. So you target that to create replica of it. Minimum 3, maximum 10. And then you need to define under what circumstances do you want me to create replica? That becomes this metrics. So the metric that we are using is going to be type resource. And the resources that we are monitoring for is going to be CPU. The target is that if the CPU utilization passes 50, create a new one. On average utilization passes 50, create a new replica. That's the idea of pod scaler here, horizontal pod scaler. Now, for this example, but if you go back to, you can see a better example here. If you go back to application scaling, so here, I didn't add this ones here, but I'm going to just show you. It's in the lab number 3, Kubernetes. So, so this is this part you saw up to this part. Now I want to talk about this behavior. So behavior means that talking about scaling up and scaling down. So you can basically indicate that. How do you want, actually, we can, let's make it easier. So let's just pick this. Bring this, add it here. So for the same thing, I added the behavior. What's behavior? It says that there are two types of behavior: a scale down, a scale up. Add more replica, remove replica. And basically, you need to, for scaling down, think about the scaling down means the traffic is now normal. You don't want to pay for this new replica that you have. What you are saying is that there is a stabilization windows per second, and you say 120 seconds. If for 120 seconds consecutive, the traffic is normal, now you can start a scale down. What do you want to scale down? I want to scale down pods, because you replicate the pods, right? One at a time, okay? Period seconds, the gap between every one, 60 seconds. So first time you wait for 120 seconds. Traffic is normal, remove one. Wait 60 seconds before removing another one, if the traffic is normal. That's basically what it says here. For a scaling up, is the same thing. I want to add, but so a scale down, you scale down slower. A scale up, you want to do faster because there's a traffic you want to answer. So every 60 seconds, you want to add 2 pods. And then another 60 seconds, another 2 pods, and so on. Yes.
So I can see that there are two types of stabilization windows. So isn't there any conflict at any time that, I mean, if something is stable for 120 seconds, it is also stable for 60 seconds. So how does it decide the window?
No, so let's say I have traffic coming through right now. These don't need to be at the same time. This one, a scale up, right now I have traffics. If I have traffic for 60 seconds, I'm going to start 2 replicas. Every 60 seconds, I'm creating 2 replicas. Now, the traffic is gone. Now I have 10 replica running, but it became 120 seconds or 2 minutes. The traffic is normal. Now I remove one at a time.
So the scale down and scale up are keywords in the YAML file for that. It's like, we can't describe it as anything else, right?
It's a behavior. It's like a fixed key, basically. Yeah. So you can find all of these terminologies in technically in the definitions that they have. So I'm going to add this maybe here also. Okay, so that was the horizontal pod scaling. The next one is the network policy. Now, the idea of the network policy is that we want to ensure that the traffic is also being controlled properly. That means only port 80 being exposed, port 8080 is from the Kubernetes. We want to be sure that this is correctly being basically transferred. Yes.
Actually, I have a doubt. Like, is this the same approach for vertical path scaling?
Vertical pod scaling, no. You need to change the machine type in vertical pod scaling. That means that in here, we are basically creating replicas faster. In the other one, you need to actually change the machine. Think about it. I have actually a good example. Let's say you're going on a road trip with your friends over there. You have one car, you're going on a road trip. Now, 4 other friends wants to go with you. And you're like, we can't fit all in the machine. You have 2 options. Sell your car by when everyone goes together. That's vertical scaling. Or rent another car, go on a vacation, come back, give it back. That's horizontal scaling. So in vertical scaling, you need to actually change the machine. It's not the same thing here.
So we have to upgrade the CPU and the.
Yeah. To update the machine, basically the types of machine that you are using. If you're using a medium, maybe you go to a large. Increase the CPU, increase the node. So it has its own challenges. It's like it's vertical, horizontal is much easier, much more like a. There's also makes more sense because you just need it maybe for a certain period of time. You don't need it always. So now here in network, basically, we create some sort of we call network policy. Backend access network policies. This policy is going to be how the front end can access the backend. That's the idea. So pod selector is going to be a backend app. Policy type is going to be ingress job. And then what we basically say that the ingress is going to be from front end. Okay, so the data that comes to the backend is going to be from the front end. Okay, and the port is going to be from port 80 TCP. Okay, that's basically how these two are going to connect to each other. So we define this manifest for the network policy that basically connect these two together. So that becomes the last the manifest that we need. Let me see. That. You need that. Okay, so now how do we, so we created this manifest, but we haven't used them actually. So what we want to do is, so in order to use a manifest in your cluster with kubectl, basically you need to do kubectl apply minus F stands for the file, has to that manifest file. For every manifest file that you have, you need to repeat the same. kubectl apply file, the address to the file. Apply them one at a time. And you can think about the order like namespace, deployment service, maybe a scaling network. Now, what I have done, which you have access to in GitHub, I have put all of those in one file, how we apply those. This command line, kubectl apply this. And I'm just going to run this sh file. It just applies all of those, okay? So what we can do, it basically, you see that it's applying, created. And when these manifests are created, now if I go back here and I go to workloads, you will see front end and back end starting. Just give it a time. It's okay. There's anomaly stuff. Or maybe. Let me check one thing on this. How many nodes we have? 1 node. Might have need to pick more nodes, but let's see. Go to workloads. Yeah, it's come up. Yes.
We define the IP for the backend when in the front end, right? So
That's a great. I didn't add it. Okay.
we have to wait for the deployment for the backend before we change that.
No, so technically yes. Actually, you need to first deploy the backend. You can basically get the IP and then use it in the Nginx. So I need to do that now. So. So if I do kubectl get service, now because we have deployed services, it tells me that there's a front end and a back end service. Load balancer, they have a private IP and they have this public IP. So if I go to the public IP, that's the IP that's being exposed. So this should basically show the app. So that becomes the app. It doesn't going to work because it cannot communicate to backend. I didn't change the IP. So I need to go back to here, pick this external IP, go back to front end index here. So that's the address to the backend. So because now I changed this, And this file was copied in my Docker, so I need to actually redeploy the Docker. Basically, I need to push the Docker image. Because this Docker image that I pushed to I3 registry uses the old IP address. So what I need to do is call this version 7. So I just created the Docker image again, and I pushed it. Okay. So if I go to let me close that. It should be version 7 over there. Now what I need to do is go to deployment and change it to version 7. Because as part of deployment of the front end, I'm pulling the image of version 6. So I changed this to version 7. And now what I can do, I don't need to redeploy everything. And you don't even need to change the service for the front end. The only thing you need to change is the deployment. Because the deployment is the one that has the address to the new version. So all I need to do is to do kubectl apply -f front end what's it called, deployment. So just give it a couple of seconds or sometimes a minute. It's starting to terminating the previous 3 because you need to remove those and add the new 3. Just wait for this 3 to be removed. The new one will come up. So it's done. So if we go to front end, and if I go down here, you see the address v7. So it now accesses to the latest image. It basically tells you that I have 3 pods ready. They are running. There is no restart. That means there's no problem. And so let's look at the summary overall. So you have these clusters, which is where you have one cluster. That cluster, if you go through it, it gives you information like some overall, the public IP that's accessed and so on. So, but if you go up here, nodes, it tells you that there is a default pool. That's the type of machine that we selected. So if you want to do vertical, you need to change this one. But then it says also that if you go down, this default pool, we have by default 1 node only, because I created a cluster with 1 node. And this is that node, okay? So, and inside that node, these are like the default Kubernetes namespaces, if you remember. These are not what we deployed. These are by default, Kubernetes has all of those. The only one we deployed was MLOPs, which was somewhere around here. So this is will be the traffic. Now, if you go to workload, you see 2 things, backend and front end. So backend, you have 3 by default are running. That's the active version. These are the managed pods. There's an endpoint address for the backend. Then you go to front end. This is the front end. So if we go here now, and let's say we say 4 plus 4, calculate the sum. Let's see. Oh, connecting to something wrong, probably. Let's look at the logs. Let's do something. Can do some debugging here. So 4 plus 4. Oh, it's just slow. So basically 4 plus 4, 8. So now what we have, we have basically a couple of things, but the main idea was for you that If you're doing a front and back end for your project, actually,